Dear listener, today's we talk about inside a black hole, so please listen carefully. Thanks. One of astronomy's greatest enduring mysteries is what truly happens inside a black hole. We know that anything venturing too close is destroyed by immense tidal gravitational forces, but what if one could journey to the very heart of a black hole? What would they find, and where would they end up? Black holes are among the most fascinating objects in the universe. They defy conventional laws of nature, existing as regions where space and time cease to function as we know them. The possibility that black holes serve as gateways to other parts of space or even new universes remains an intriguing yet unproven hypothesis. Today, we explore what may lie on the other side of a black hole. The nature of black holes. To understand how a black hole could act as a gateway, one must first grasp the fabric of space and time. According to Einstein's theory of general relativity, space and time are intrinsically linked, forming a malleable cosmic fabric known as space-time. This fabric is warped by the presence of mass. Greater mass results in greater curvature, which we perceive as gravity. If enough mass is concentrated within an extremely small volume, space-time deforms so drastically that it forms a bottomless sinkhole, a black hole. At the core of every black hole lies a space-time singularity, a point of infinite density where conventional physics breaks down. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. Once past this threshold, all paths lead inevitably to the singularity. The interior of a black hole. Inside a black hole, space and time switch roles. Time flows inexorably towards the singularity, meaning that reaching it is not just a possibility but an inevitability. However, due to the extreme warping of space-time, an observer falling in would perceive time stretching infinitely, never actually reaching the singularity in a finite amount of their own time. This raises an intriguing question: could a black hole connect to another part of space-time? Some theories suggest that an extreme warping of space-time could create a bridge, an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical structure could link two distant regions of space, allowing for instantaneous travel between them. Wormholes, the cosmic bridges. While wormholes are consistent with general relativity, their existence remains purely theoretical. If they do exist, they are likely to be highly unstable. The immense gravitational forces within a black hole would likely cause any wormhole to collapse almost instantly, severing the connection before anything could pass through. Even if a stable wormhole could form, it would not provide a practical means of travel. The extreme time dilation effects of a black hole mean that an object entering it would be effectively frozen in time relative to the outside universe, making traversal impossible in any meaningful sense. The white hole hypothesis. A more speculative but related concept is the white hole, a theoretical counterpart to a black hole. If a black hole consumes matter, a white hole would expel it. In principle, a black hole's event horizon acts as a point of no return, while a white hole's event horizon is a barrier through which nothing can enter, only exit. If wormholes exist, a black hole could be linked to a white hole, forming a cosmic passageway between 2 points in space-time. However, no definitive evidence for white holes has been found. They remain a mathematical curiosity rather than a confirmed reality. Searching for white holes. Despite their theoretical possibility, white holes have not been observed. If they do exist, they may be exceedingly rare or short-lived. They would resemble black holes from a distance, with one key difference: rather than consuming matter, they would expel it in brief, violent bursts. However, such events would be difficult to distinguish from other high-energy cosmic phenomena. The place where time stops, and the singularity becomes the infinite future. However, this black hole is eternal, meaning we must account not only for the infinite future but also for the infinite past. Extending our diagram backward in time, we encounter a time-reversed black hole, one that only ejects matter and energy. The singularity now exists as an event in the infinite past, forever unreachable. Trying to reach it would be like attempting to travel backward in time. Instead, light and matter can only flow outward, away from the singularity, into the universe. And thus, we have our white hole. Connecting the two horizons is our Einstein-Rosen bridge, a hypothetical passage that may lead to another part of space, another point in time, or perhaps an entirely new dimension. But despite its theoretical elegance, the case for a white hole's existence is unconvincing. The concept is merely the eternal black hole viewed in reverse, without any physical necessity for a white hole counterpart. Moreover, the eternal black hole itself does not exist in practice. Black holes are born within a finite span of time and eventually evaporate due to Hawking radiation. A black hole's time reversal, in reality, is not another black hole but rather the object that formed it, a collapsing star, a contracting gas cloud, or merging neutron stars. While general relativity allows for wormholes and white holes, it is a time-symmetric theory. It does not distinguish between past and future, nor does it account for other fundamental laws of physics, such as the second law of thermodynamics. There is no known mechanism that could create the highly ordered energy of a white hole from empty space. Coupled with the absence of observational evidence, white holes remain a concept that resides more in science fiction than science fact. That said, wormholes might still exist, perhaps flickering into existence for brief moments or hidden in microscopic forms predicted by string theory. But the idea of white holes bursting through to other regions of space is unsupported by science. One could argue that our search methods are insufficiently advanced to detect wormholes, but overall, the disappointing conclusion is that wormholes and white holes likely remain theoretical constructs. This, however, does not necessarily mean black holes lead nowhere. While we've never observed a white hole, something in the universe does mimic its behavior: the Big Bang. The Big Bang was a singular event where an immense amount of energy was released, expanding outward ever since. Even today, galaxies are being pushed apart by a mysterious force, much like how a white hole would be expected to repel matter from its event horizon. A white hole's event horizon is essentially a temporal boundary. Trying to breach it would be akin to traveling into the past. Similarly, the Big Bang represents our universe's own temporal limit. Nothing can precede the moment of its inception, as time itself came into existence at that moment. The resemblance between a white hole and the Big Bang is intriguing. We know little about why the universe exists or what gave rise to it. If black holes are somehow connected to the Big Bang, then perhaps what we call a white hole is actually the birth of a new universe. This perspective completes our cosmic diagram. When extending both past and future black hole solutions, the Einstein-Rosen bridge does not lead back to another location in our universe, as a wormhole would. Instead, following the negative square root solution of the Schwarzschild metric beyond the black hole's interior leads to an entirely new universe, a parallel universe where time flows backward, forming what is known as the maximally extended Schwarzschild solution. One line of thought suggests that rather than being mere portals across space, black holes could be the birthplaces of new universes. Perhaps our universe itself was born from a black hole, with its resulting white hole manifesting as the Big Bang. This notion leads into the concept of black hole cosmology, which suggests that universes are born within black holes, creating a vast, branching multiverse. In this model, universes capable of producing black holes are naturally selected for survival. Thus, our universe may be typical among countless others, but we may never know where this cosmic lineage began or where it ends. According to this idea, matter falling into a black hole does not travel to another point in space but instead compresses further and further toward the singularity. Eventually, at an extreme but finite density, it rebounds, giving rise to a new Big Bang and expanding universe. Beneath the event horizon, space-time curvature becomes so extreme that the new universe has infinite time and space in which to evolve, birthing its own black holes and continuing the cycle of creation. If this is the correct cosmological model, it could provide insights into key questions about the nature of the universe, what lies beyond it, and what it is expanding into. In this view, our universe is merely the interior of a black hole from a larger parent universe. This hypothesis would also explain why our universe's origin, a single point of infinite density, bears such a striking resemblance to a black hole singularity. Despite their forbidding exteriors, black holes might be the cradles of new universes. Thus, even if wormholes do not exist, something could still emerge from the other side of a black hole, shaping the fabric of reality in ways we have yet to understand. Even if white holes are merely mathematical artifacts, they might still provide clues about our origins. Ultimately, we do not know the true nature of black holes. Any one of our speculative theories could hold the key to understanding reality. Perhaps black hole cosmology is correct, or perhaps it is entirely mistaken. Maybe black holes lead nowhere and merely imprison matter forever in a cosmic purgatory. Unfortunately, we may never uncover the truth. Their very existence outside conventional space and time renders their secrets elusive. However, even if black holes do not create new universes, there remains one final possibility for a white hole, one that does not require wormholes or new dimensions, but only time. Stephen Hawking and others have shown that black holes slowly leak mass and eventually evaporate over extraordinarily long timescales due to quantum fluctuations. Virtual particle pairs constantly appear along the event horizon, with one falling into the black hole and the other escaping, taking a fraction of the black hole's energy with it. After an immense time span, a black hole will shrink to a minuscule size and mass. As a black hole diminishes, its temperature rises inversely with its mass. Eventually, it becomes hotter than the primordial plasma of the early universe, an unimaginably energetic state where the fundamental forces were unified. In its final moments, its radiation may become so intense that it overcomes the singularity's gravity. At the black hole's last breath, all of its remaining information could be expelled, irreversibly radiating outward, much like a white hole would. Thus, even if wormholes and parallel universes do not exist, white holes may still illuminate the universe in the far future. Long after stars have faded and galaxies have dissipated, they could serve as the last beacons of light in an otherwise darkened cosmos. What a spectacular sight that would be at the end of time. Please like, share and subscribe my channel. Thanks.